Hi, my name is Randy Becker. I'm an application engineer with Keysight Technologies. Today I'm going to show you how to use our Signal Optimizer software. This software does three important things. It can generate signals, it can analyze signals, and most importantly, it can calibrate right to the device plane of interest. Our customers have told us that calibrating is a big job for them, and the reason this is important is that you want to see the true characteristics of your device under test. You don't want to see the characteristics of the cables, adapters, and test equipment. And so we'll show you how to use the software to make measurements right to the device plane of interest. Now let's take a look at the demo setup. In our demo setup, we have an arbitrary waveform generator, the M8190. This is connected to the PSG, which upconverts the analog IQ signals up to the frequency of interest. This can be anywhere from a few megahertz all the way to 44 gigahertz. In this demo, we're going to use 28 gigahertz. This is connected to a signal analyzer, the UXA, which has 1 gigahertz of bandwidth. We'll use that to digitize the signal and then make measurements. Also, we have a comb generator. This is what enables us to do the calibration. This generates an extremely wide bandwidth comb signal all the way up to 67 gigahertz. We know the exact amplitude and phase of each of those CW signals coming out of the comb generator, and that's what enables us to do the initial calibration on the receive part of the test setup. Then we'll do a calibration of the source side as a second step. Now we'll look at the software which ties all of this together. Okay, so let's take a look at how the Signal Optimizer software actually works. At the top of the screen you can see a block diagram approach for the entire measurement system, and on the far right you see the calibration wizard. Since this is the most important part about the Signal Optimizer software, we're going to start with that, then we're going to come back and generate and analyze some signals. So I'm going to click on the calibration wizard. We have three different types of calibrations we can choose from. We can choose to do a source-only calibration, we can do an analyzer-only calibration, or we can calibrate both the source and the analyzer. And this includes anything between the device under test and the measurement equipment. So this could be cables, filters, amplifiers, etc. So in this example, we're going to do the full source analyzer calibration. At the top here, we can set the frequency, and in this example, we want to use a frequency of 28 gigahertz. So I've set that to 28 gigahertz. We're going to calibrate over the full bandwidth of the measurement system. So in this case, 1 gigahertz. We're going to set the source amplitude to -7 dBm. And then we're set the analyzer input range to about -4 dBm, which we determined earlier was the right range for the cable loss we have at 28 gigahertz. On the bottom part of the display, we have some more detailed settings for both the analyzer calibration on the left and also the source calibration on the right. The most important part on the analyzer side of the configuration is selecting the comb generator that will be used. This is going to create the test signals that we will use to calibrate the analyzer with. And so we see here the model number and serial number of the comb generator. And then on the right side we have the source calibration settings, and we want to enable the corrected results on the analyzer side when we do the source calibration. This is what enables us to make two different test planes at the input and output of the device under test. So when we do the source cal, we want to include the newly calibrated results of the analyzer, which could include all of the cables and adapters and test fixtures. So once we've chosen the settings, we say start the wizard, and you'll see here a simple block diagram for how to perform the calibration. What we need to do is connect the comb generator to the input of the analyzer, which can include all of the test fixturing. In this case, we're just going to use a cable. So I have that done. Now I say next. If I wanted to make changes to the frequency, bandwidth, etc., I could still do that here. This information is still on the display, and I still have access to those detailed settings if I need to. But We're satisfied with the current configuration at 28 gigahertz, so we'll say calibrate point. And it's going to go ahead and make a couple of measurements. And you'll see the channel response both in magnitude and phase after the calibration's done. We see on the upper graph the magnitude response, including all of the things in our test system. And on the bottom, you see the phase response. And so it took a couple of measurements, and now we have a nice, clean, stable result. So then we'll say next. And now it's basically telling us that we need to connect the analyzer directly to the source hardware, which again could include any of the cables, adapters, and filters that might be in the signal path. Okay, so I've reconnected the output of the generator to the analyzer, and I say next. And now I'm going to perform the calibration again. So now we're calibrating the output of the signal generator, including all of the test fixturing, up to the device under test plane. So this will make two measurements. The first measurement will show us what the uncorrected response looks like. On the top here you see the yellow line shows the uncorrected response of the system. The green shows the response after the calibration. And you can see the amplitude response is basically flat line after the calibration. The bottom graph shows the same information, but for the phase. And again, there was some phase response due to everything in the test system, but after the calibration, the phase response is very flat. The right graphs show the calibration in terms of the imbalance between I and Q. So this is everything to do with the IQ signals up to the IQ modulator. And you can see before and after the calibration that in this case everything was very well balanced, both in magnitude and phase. We're satisfied with our result, so we can say next, and then basically finish the calibration. Now that we've calibrated the system, let's actually use the software to generate a signal and then analyze it. And we'll do this for two types of signals. The first one, we'll use a simple single carrier 16 QAM signal, and then we'll do a pre-5G waveform. At the top of the screen, we'll start with the signal block, and I can choose to add or delete various waveforms to my configuration. So in this case, I'm going to choose to do a custom IQ. I could add multiple waveforms to my configuration to create a multi-carrier waveform. But for this first one, we're going to do a single carrier waveform. So now that I've added that to my configuration, I'll click on it, and then I have all of the settings available pertinent to that configuration on the right side of the screen. What I'm going to do is change the symbol rate from 50 megasymbols per second to about 700 megasymbols per second. And this will give us almost 1 gigahertz of bandwidth when we have a root raised cosine filter of 0.35. And in the bottom here you can see the default is already 16 QAM. When we added this signal to our configuration, it also added a corresponding measurement. So all of the settings were auto-coupled to the measurement, so we don't have to redefine that again. And we'll see that when we get to the measurement part. But let's continue on following the flow of the block diagram. So the next part would be the source hardware. So I can click on that, and here I can set all the various things related to generating the signal. I could set the frequency, the amplitude level, and so forth. What I'm going to use here is 28 gigahertz. That was already the signal I was generating. The amplitude is -7. You have various other details, but for just generating a simple 16 QAM signal, this is sufficient. Oh, one more important thing. I can choose to apply a calibration. I'm going to set this to automatic. So the software knows, based on the configuration of the hardware, what calibration will be applicable. You could set this up for different frequencies, different amplitudes. Have you already done a calibration at that frequency and amplitude? If yes, I can apply that calibration. So you can choose to have that done automatically, or you can manually override it and apply a particular calibration. Once I'm satisfied with the configuration, I can download by pressing this button. So it'll download all of the settings to the arbitrary waveform generator and the signal generator, and it'll automatically begin generating that signal for me. So it's loading that to the ARB. Then the next block that we would deal with is the analyzer hardware. And here we can see that the frequency and bandwidth have automatically been coupled based on our source settings. We could override those. Perhaps we might have something that has like a mixer if there was some frequency translation. But in this case, we're doing this at the same frequency and bandwidth, so we don't need to change anything here. And then we'll go to the measurement block. And here you can see the time and spectrum view. The bandwidth is indeed just under 1 gigahertz. So we're generating and analyzing a very wide signal here. And now let's look at the demodulation results. So here you can see the 16 QAM signal, and it doesn't look so good. Our EVM is around 6-7%. And that's because we haven't applied the calibration to both the source and the analyzer. So let's go ahead and do that. So if I go back to the source hardware, I can select the source corrections. I can turn that to automatic, and it will apply the calibration that makes the most sense for this configuration. It knows that I've done a calibration at 28 gigahertz and a gigahertz of bandwidth, so it's going to use that calibration that I had done earlier in the automatic setting. After we apply that calibration, or actually I need to download the signal to include the calibration file. This is really a pre-correction that we're doing to the waveform to calibrate the signal at the input to our device under test. After I apply the calibration, you can see the EVM went from about 6 or 7% down to about 4%. So things are looking a little better. And the last thing we need to do is apply the calibration to the analyzer. So let's go to the analyzer hardware. Let's go ahead and set it to automatic. And now you can see our EVM has dropped to less than 1%. So here we're at about 0.8 or 0.9% over 1 gigahertz of bandwidth. So this is a fantastic result at 28 gigahertz. So let's take a look at a multi-carrier pre-5G signal. We'll also generate this at 28 gigahertz. And since we've already calibrated the system, we don't have to do the calibration again. We're free to try different waveforms, different modulations. And so we're going to go for the pre-5G waveform. So let's go back to the signals block and change our signal. Now I'm going to add a different waveform type, and I'm going to use the file import. So if you've created a waveform, say in MATLAB or C++ or one of our other Signal Studio applications, you can actually import those using the file import function. And now I have two different waveforms that would get added together. Since the file that I'm going to import is actually a multi-carrier waveform, I'm going to delete the custom IQ waveform that I'm currently generating. And I will configure the file import. So I'm going to set this to the waveform file type, since this was generated from one of our Signal Studio applications, and I'll select the waveform. So I'll do that here on the desktop. I'm going to select a 8-carrier signal. Each of the carriers is 100 megahertz wide. And I'm also going to load the setup file from the Signal Studio application. So this will take all of the settings from Signal Studio and apply them to the demodulation for us. So now let's take a look at the measurement of our 8-carrier pre-5G waveform. We're looking at the time and spectrum view, and you can see, in fact, there are 8 carriers here, and they occupy approximately 100 megahertz each for a total bandwidth of about 800 megahertz. Now let's look at the demodulation metrics. So if we go to the OFDM demodulation, you can see that the carrier that we're demodulating is 64 QAM. Actually, all of the carriers are 64 QAM. On the right side of the screen, you see the channel response in terms of amplitude. And you'll see this line is almost a straight line. That's because the calibration that we did of both the source and the analyzer are extremely accurate. The scale here is 0.5 dB per division, so this is a very good result. Likewise, on the bottom, we're also showing the phase response. And the scale here is 1 degree per division. So virtually the effects of the channel have been eliminated. We've accounted for all of the amplitude and phase characteristics through the entire system. And now if we look at the EVM result, we have an EVM of just about 1%. So this is a great result of an 8-carrier pre-5G waveform. If you have any questions, visit the URL on the screen or contact one of your local field representatives. Thanks for watching.